Okay, we're going to continue with the table. I just want to point out a couple of other things to you that you can see that the target in uh, 2020 is 12%, and that seems ambitious according to these data. But if we were going to, and I want to get back because we are talking about population groups, I want to talk to you about the values that I'm going to be using in this population problem. So, but I did want to reflect on this table because I think it's pretty telling. And you can see by looking at the table that let's just take the last year. Um, that if you're looking at educational attainment, that the lower the education, um, the greater percentage of smokers. So if you have an advanced degree, you can see that it's very unlikely that you're going to smoke. Doesn't mean that you won't, but it's unlikely. And family income, the the more you're under the poverty level, um, you're going to smoke. And so we draw conclusions pretty quickly. We can see that if if you're a low income person, if you're not particularly educated, and that if you just look at the age aspects, we're going to see that those what 18, I guess it's a better indicator is 40. Well, my apologies to you here. This is doesn't give us very much information about age. Age doesn't seem to be really a contributing factor, but you can see the sex difference. So males still smoke more than females. But what's really interesting is what you note here. You notice a tremendous drop from after age 65. I'd like you to think as to why would this occur. And I wonder if you have any ideas. And what we note, or we come to appreciate and recognize, that smokers are dying after the age of 65, and that's what this data reflects. So, and then we could do it occupationally and look at the professions or the occupations where people smoke the most. Now, they do have a CI or confidence interval of 95%. So if they were going to draw this data, a sample of this data, 95 times out of 100, they come up with the same value. So we have pretty good confidence that this data is important. Now, the number that we're going to be using for our problem is going to be the total population or the percentage of smokers, which is 19%. So, going on to the next slide, we're going to calculate the population statistics because we've already done the group statistics, and this is not nearly as difficult as what it seems. So you just flow with me, and I think you'll find that things go together rather nicely. But we're going to calculate the attributable risks for the exposed group, attributable risks for the population taken from a secondary source. We know that 19%. We know that 19% came from a secondary source, and that happened to be from the CDC. And attributable risk in the population is which is due to exposure can be calculated by subtracting incidence in the population and incidence in the non-exposed group. Okay, now this is, notice the word population because we're going to be using values here from the population to calculate incidence rate, and we're going to use values here, you'll see very quickly, but we're going to use group data um, for the comparison group. So to calculate, you must either know the incidence rate in the total population, or the incidence rate among smokers, or the incidence rate among non-smokers, and the proportion of the total population that smokes from which the incidence rate in the exposed group can be calculated. Well, we know this, right? This is what we got from this secondary source, and we talked about where we can get this information. We went over that table pretty thoroughly, and you can go back and look at it. And based on the current population, or our current information, I should say, we really do know all of this. We know the incidence among smokers in our group is 28 per thousand per year. We know the incidence of non-smokers from our data is this, and the proportion is 19% as denoted in the Healthy People 2020 document. Now let's watch what happens to this data to make adjustments to see whether our group really represents the population or not. Okay. Assume from this secondary source of information that the proportion of smokers in a population is 19% and 81% for non-smokers. Well, you say, where do we get the 81%? Well, if 19% smoke, we're going to subtract that from 100%, and that would leave us 81% who didn't smoke. Okay, so that's simply where that value comes from. Now, notice how we substitute the numbers in. We substitute the 19% in. We're going to do a calculation. We're going to multiply it. And this is our group data. And we're going to take the non-smokers, and we're going to multiply it by this factor, and we're going to add these two together because we're going to use this value in our calculation. Okay? Next, what happens, we ask what the attributable risk is for the incidence in the total population and incidence in the non-exposed group, and here's what we have. Excuse me. We've done the multiplication, and here's the value. This value is being shifted and used here. We're always going to take the non-smokers and use them as a secondary value. So the attributable risk in the problem is 2.0. Okay. Now you may realize before that the attributable risk was 10.6, so it's dropped quite a bit. So we are beginning to wonder at this point. We're thinking to ourselves, well, maybe the population, or the group sampling procedures, or the group that we used and then we sampled from, is not a very representative group. Now let's just go on and we'll do the other calculations, and you know this. It's the same, except we're going to look at the incidence rate in the total population and the incidence rate in the non-exposed group. So we're going to use this value here. We're going to use this value here, and we're going to again use this value here. Just check me out and see whether I'm correct. Okay. So instead of 37.9, we have 10.3. So there should be a total reduction of 10.3% in the incidence rate of coronary heart disease in this population if smoking were eliminated. Well, that's a huge difference in terms of what we got before. So our sample is not very representative of these better data from the United States, all over the United States in terms of the proportion or the percentage you smoke. Okay, now all we're doing is the same type of thing. Now notice I'm doing a group versus population comparison in terms of attributable risk. Okay, and this is always our baseline amount or our endemic state. And so when we take away that background, this was a group data, we had 10.6, right, um, per 1,000 per year. When we look at the population, we had 19.4 versus 17.4. We came up with 2, so the attributable risk was here was 2, and this was 10.6. So we did the calculations here as we did the calculations here to come up with a 10.6, and we'd already done this. So the difference between the group and the population is 8.6. So that's a big difference in terms of attributable risk. That means you're less at risk by using the population information than you are the group information. We would believe and say that we would have more confidence and this would be a more valid score than this one, because this is based on the total U.S. population, where this is based on a small group of people. Okay, relative risk. We ask, is there an association between exposure and disease? If so, how strong is the association? And relative risk answers those questions. So if we look at it, and absolute risk, so you know that that's incidence rate among the exposed group, and absolute risk or incidence rate among the non-exposed group. It's a very simple statistic, right? There's nothing that's particularly complicated about it. It's just simple division. Okay? So, again, we have relative risk, and here's the formula for it. And in our problem, we could use, for the group, we would have a relative risk of 1 divided by the other, which would give us 1.60. Now let me interpret this for you. A 1 is a null hypothesis, which means there's no difference in risk. And since it's 1.61, we would say that just dropping the 1 off, that it's a 61% increase in risk over 1, or it's 1.61 more than the unexposed group. So you can talk about it in two different ways. You can say it's a 61% increase, or it's a 1.61 more or greater than the unexposed group. Okay? Now, when we look at this, this is how we look at values, and I want to take this slowly with you. If we get a value here, let's say this is 0.78. The relative risk is 0.78. That means it's a protective factor. That's a behavior that you ought to engage in. Let's say it's 0.54. That's something that you ought to do. And sometimes we find that the relative risk for exercise falls into these numbers under 1, or the null hypothesis. And if it's greater than 1 in this particular case, you're at risk. But we don't consider, generally what we consider a critical value for you really being at risk is 2, which means you're 2 times the risk for a particular risk factor. So you're double the risk. So that's another way to say it. An odds ratio, we use an odds ratio comes out with a score very similar to those that have been, well, identical to these scores that I'm reporting here, and you interpret it in the same way. Okay? And an odds ratio is a good estimate, a good estimate of relative risk, because we know the Cadillac, the best is from a prospective study. It says when the cases studied are representative of all people with the disease in the population from which the cases were drawn with regard to the history of exposure. And we already talked about a group that we selected that wasn't very representative of the population. We just showed that. We went through that process. The controls studied are representative of all people without the disease in the population from which the cases were drawn with regard to the history of the exposure. And the disease studied is infrequent. So when you're going to use an odds ratio is when the disease studied is infrequent. So when you're going to use a cross-sectional design, when you're going to use a case control study design, where you're going to use a historical perspective design, you use those when the disease being studied is infrequent. If it's a rare disease, you don't want to use a prospective study because it takes too long for the disease to develop and it's too expensive of a process. So I hope that is clear to you. Now, so here's just a little quick review for you. RR is calculated directly. It's a gold standard. RR cannot be calculated directly and can be termed relative odds, although we don't calculate relative odds for a prospective study, not when you have the gold standard of relative risk. So with an odds ratio, which an odds ratio is an estimate of relative risk, and we designate this as OR versus RR. So, and I'll show you in a minute that this is just a multiplication of cross products and is used again as an estimate of relative risk. But this would be designated OR versus RR. And we do not calculate relative odds, which we could, and I'll show you relative odds would be calculated the way we calculate an odds ratio. Okay, I told you that there was 3 tables that you needed to know, that you needed to take a snapshot from. And this is an odds ratio for an unmatched design. In other words, we're drawing people at random and they go into one group or another, and so we're not trying to match people on a set of demographic variables and then to do our statistics based on them, and I'll cover that so you know it. Okay, now, so you obtain an odds ratio from a case control, historical perspective, or cross-sectional study. And an odds ratio is the multiplication of cross products, okay, divided by the multiplication of those cross products. That's an odds ratio. And you know relative risk is not calculated this way. Okay, so let's look at the next slide. Okay, this shows And I want you to notice layout of the table again. Cases with the disease, controls without the disease, were exposed, were not exposed, and the multiplication of cross products. And this is how we calculate an odds ratio for unmatched pairs. Okay? So I want you to be certain to notice the the headings in comparison to the prior table for relative risk. Note that the proportion of exposed in the lower left corner, which is really focusing indirectly on attributable risk. But normally you don't see it, normally you don't calculate, you only calculate one value for a case control study of unmatched pairs. Okay? So let's try this together. Now notice this layout of the table. The total really is in the wrong place. It should be the total here. This is just a sort of confuse you a little bit, and because I don't want you to get used to looking at values in a certain place and thinking that you ought to be using these values in the multiplication of cross products. That would not be appropriate. So we'd probably move the total down here. Now, first select cases with coronary heart disease and controls. Then determine past exposure to smoking. And then you would do next a multiplication of cross products. And notice this is how it's done. And the multiplication and the division. And the odds ratio is 1.62. Now you interpret that 1.62 the same way we did for relative risk. There's no difference in that. There's no difference in that interpretation. So it's an estimate of relative risk. And we talked about when it is a good estimate. And this study is much less expensive than a prospective longitudinal study. And but otherwise you only get one statistic from it. You don't get four like you did from the prospective study. Okay? And I want you to notice that we have cases and controls. So this is a case control study, and then we determine based on the past exposure to smoking and non-smoking by looking at medical records or by some particular means to determine whether they're a smoker or a non-smoker. Now let me add one other thing that's important that often is overlooked. We want to take the exposed group should be those who have the highest exposure, and the non-exposed group or unexposed group would have the least exposure. So if we could take people who smoked 3 packs of cigarettes or 60 cigarettes a day and compare those who don't smoke at all, that's what we want to do. We don't want to do the least comparison first. We don't want to take a group that only smokes 1 pack and compare them to those who do not smoke any cigarettes. What we're trying to do is we're trying to determine whether there is an association. And so if there's the association is likely to occur under the worst condition or the greatest smoking frequency. Okay? And that's an important point to remember in all of this. And I don't want you to forget that, because that's just what goes on. Okay, what is the effect and what does it mean? Well, this number is greater than the null hypothesis, which is 1, right? And it's 0.62% increase. there's a 0.62% increase over the null hypothesis of 1, or a 1.62 or 1.62 more risk than the non-exposed group. Or another way you could say it is 161% higher risk than the controls. So you've got three ways that you can say that. All of them are correct, and you might familiarize yourself with those. So we can say it's a 62% increase risk over the null hypothesis of 1, or it's 1.62 more at risk than the non-exposed group, or we can say it's 1.62% higher risk than the controls. Okay, and notice how I've made every comparison in reference to the information on the table. Okay, so I've not gone outside the source of information that's presented here. Now, what does this mean? Well, this is not very much of a risk. We said anything over 2 was meaningful. Now, people said, that's double the risk. And people said, well, what is the highest value you've ever seen? The highest odds ratio or relative risk value I've ever seen is 16. And that's probably a behavior I would not engage in. That tells me that that there's great risk, that there's substantial risk, and a behavior that would cause ill effects, is likely to cause ill effects to your health. Now, I couldn't go much further than that based on one study, but if 2 is bad, 16 is a lot worse than 2. Okay? And you could put it into the percentages and relationship to the null hypothesis, and go through the same process that I've done here. And you might want to do that just to see whether you could interpret the 16 in the ways that we've talked about thus far. Okay. Next, calculating the odds ratio in a matched pairs case control studies. I want to read this to you. Controls are often selected by matching each control to a similar case based on common demographic variables plus other variables found in the research literature that are known to be important. Below are some of the variables that probably would be included in related to disease, and I share these with you. Okay? Sex, age, race, socioeconomic status, whatnot. Or, you could talk about devoutness in terms of religion. Okay? Or diet. 7-day Adventists were very important and brought a lot of information to us because they were vegetarians or vegans. I can't remember which, but that study's been done some time ago. Okay, so there's so I could match these subjects on. Let me back up here. I could match these 2 subjects on. One would be a case, one would be a control on sex, age, race, and socioeconomic status. Now, the more of these variables you take into account, the more difficult it is to find a control case, a control that is similar to the case that you're going to do the comparison against. So this just but you are taking these factors into account a priori and ruling them out because you think, based on the research literature or other reasons, that they may bias the findings if we don't match subjects, and therefore eliminate these variables as a source of bias or error. Okay? Now, what we're interested in is the discordant pairs, but let me cover the concordant pairs. The concordant pairs, pairs in which both the case and the control were exposed. They're not going to tell us much in this case. Pairs in which neither the case nor the control was exposed. Okay? The discordant pairs, they're going to tell us what's wrong. They're the most important of the two sets of pairs. Pairs in which the case was exposed but the control was not. That's interesting. Pairs in which the control was exposed but the case was not. Okay? And again, when you're following an epidemiologic approach, you're organizing data into a 2x2 contingency table, A, B, C, D, as we have seen before. And we're interested in the pairs that don't get along. The first two pairs we used to call these lovers and these quarrelers. So if you want to think of a relationship, these folks get along, these folks don't, but these are the ones that are going to inform us about the degree of exposure and how big a problem it is. Okay, so now, this is so important. Study the layout of this table. Usually when we have a case control study, the case comes up here and the control slides over. Now, that was for an unmatched pairs design. Now, for a matched pairs design, the cases are located here, and the controls are located on the top. So we have diseased. This is the concordant pairs, and we have non-diseased and non-diseased, and this is a concordant pair because they get along, right? And then when we go to non-diseased and diseased, this is a discordant pair. And then when we go to diseased and non-diseased here, we have a discordant pair. So all we need for this calculation for a case control matched pairs design are the discordant pairs, and this is how you calculate the odds ratio in this particular case. Okay, and odds ratio in a matched pairs study is based on only B and C are the arguers, those that don't get along, those that are discordant. Okay? Now, further, the concordant pairs I mentioned are A and D, and we ignore those. They're not going to provide us any information because they agree. And if we went further, the odds ratio for matched pairs is a ratio between the number of pairs in which a case was diseased and the control was not, B, divided by the number of pairs in which the control was diseased but the case was not. Okay, now I want to take you through a problem. Okay, let's see whether we can do this together. I want you to assume a study of cases and controls in which each control was matched to a case resulting in 10 pairs. Assume the following findings were E equals exposed and N equals non-exposed. So which ones are we going to be interested in? Well, this is a discordant pair, isn't it? And so we have exposed and non-exposed. So let's see. Let's just count these. So we would be interested in this. Let's not count them. Let's just look at, we'd be interested in this. This is a concordant pair. We're not interested in that. This is a concordant pair. We're not interested in that. This is a discordant pair. We're going to be interested in that. This is another discordant pair. We'll be interested in that. We won't be interested in this because they're a concordant pair. This is a discordant pair. This is a concordant pair, and this is a discordant pair, and this is a concordant pair. Okay, so let's count discordant pairs. Those are the ones we're after. So we got 1, right? We got 2. We have 3, and we have 4. Okay, so for cell B, we're going to have a 4. Now, we've got one other discordant pair where the control does not agree with the case, and that's case number 5. So that is 1. Okay, so we only have one in which the control doesn't agree with the case, and we have 5 cases that don't agree with the controls. So for our calculations, what we would do is we would fill out our cells. I didn't even bother to count the other ones because we're not interested in the concordant pairs. We're just interested in the discordant pairs. And this happens to give us an odds ratio of 4.0. So you can go through and read all of this to see why how you'd classify the others that have the same letters. Okay? So our odds ratio with a matched pairs is 4.0. Now, I want to show you something else, and that leads you to the reason that they're ignored. And we did our odds ratio with discordant pairs. But we could go on and do a case control unmatched. And I'm going to go back and show you how we're going to do this, okay? And you can go back and do it yourself, and we'll come back to this. Okay. Cases and controls in which we have exposure and non-exposure. So we have 1, 2, this is unmatched now. 1, 2, 3, 4, 5, 6. Okay? And that's going to go in cell A. So we got cases with the disease that are exposed. And then we got cases that are unexposed. 1, 2, 3, 4. And that's going to go in cell C. And then we got controls without the disease. Let's see, we got 1. Controls without the disease, we've got 1, 2, 3. Without the disease, or controls with the disease, exposed. We got 1, 2, 3, and we know there are 10, so we got, so this would go in cell B, the 1, 2, 3, and then we subtract that from 10 because we know there are 10 there. We would have 7 in. So 1, 2, 3, 4, 5, 6, 7, and those would be unexposed controls without the disease. Now let's go back over here. I want to show you what I've done, and this would be a case control unmatched study, and we would come up with results like that. If we did it that way, for the matched odds ratio, we would come up with a 4, and when you subtract the match from the unmatched, it's 3.5. So we have gained 0.5 risk in terms of matched and doing a matched odds. In other words, let me go back and I'll come back to this in a second. In other words, it tells us that these variables were very important to control because they had some influence on the degree of risk. And by controlling them and matching cases and controls, we gained a risk of 0.5, and because those were confounding variables, and the true risk, the risk we would report, is 4. And this would be a high risk because we said anything over 2 is substantial. So the suppression effect is how much influence the matching variables had on the odds ratio. If we use a few matching variables, we don't know which one had an effect, but one of them did have. And so we would have an interaction of those variables working together that would have greater risk. Okay, I think that concludes our statistics related to research designs, and the next topic I will introduce to you is causality.